We're moving on from Lake T today. We're getting into an estuary model, so we're going to be talking about some aspects of how we might set up a coastal estuary model here. And then later today, we're going to be getting into sediment transport and wind wave modeling. So just to go over the conceptual framework as we have done in the previous lectures. First, we have just some reminders to check out the user's guide, the knowledge base, and the theory document as well, if you have questions. So estuaries are an interesting kind of system to model. You can have a lot of different factors affecting the behavior of what's going to be happening in your estuary. You might have freshwater inflows that might be really significant for dictating the characteristics of how the estuary functions, or they might not be. Direct runoff, this could even include industrial discharges, or really any kind of mass flux into the model domain. Wind and waves, we're going to be dealing with the wave aspect of that a little bit later, but in most cases, wind is going to be a pretty important factor, especially in very slow moving estuaries, for inducing momentum into the water that can drive mixing. Tidal action, we're going to be discussing how you would use an open boundary condition today. That's pretty much the only way to set up a coastal model because usually you can't quantify the amount of flow in and out of an ocean boundary. It's just not something you can really measure. Wave breaking and longshore rip currents. So we can predict the formation of rip currents and longshore currents. Wave breaking, that's something that is handled by a little bit more advanced wave modules than are built into EFDC, but we'll still talk about those a little bit later today. And then, out in the coastal part of your model, you can assign boundary conditions for waves themselves. So you can take into account any kind of swells or anything that might be coming into your model domain, which might affect the behavior of your system. So one feature of estuaries that can be kind of challenging from a modeling perspective is handling of wetting and drying. As I showed you yesterday in the hydrodynamic settings, we have a good amount of control over how much time EFDC is going to wait before it will check if a cell is wet or dry again. If you have an estuary or a coastal floodplain that's got a lot of cells, say you know that this area maybe at high tide is all wet, you still want those model cells in your domain, but you know that you don't always need to be looking at them to see if they're wet or dry. So you can save some computational effort in that regard using the dry step setting in the hydrodynamics tab. Freshwater discharges, these are mostly going to be the same kind of setup that we looked at for Lake T, just simple time series. Direct runoff, you may be able to apply some simple engineering equations just using impervious area and rainfall intensity to compute these, or maybe you bring in a more advanced hydrologic model in order to make those predictions. Salinity gradients are a huge factor in a lot of estuaries. Often the intrusion of salinity into an estuary is a topic that we'll be concerned with in our modeling. Of course, the transport of sediment, as we're going to be getting into a little bit later today, can be really important for navigational considerations, navigational safety. Dredging, of course, is typically associated with those changes in the navigational characteristics of an estuary or harbor. Depending on how large your estuary is, the Coriolis force might be a factor, and that will affect the rotation. That will induce a rotation in the water body that you'll see in the velocity patterns. Again, depending on how large the area of interest you have is, the differential pressure throughout the model domain might be a factor as well that you want to consider. So wind and waves, we've discussed those. Propeller wash, that's a big topic that we are concerned about here, especially in a lot of harbor areas where large container vessels might be sitting at berth with their propellers running, or might be warming up to push off and be kicking up sediment all that time. Depending on what's in the sediment, that might be a problem. And then, of course, climate change, storm surges, sea level rise. These are all things that we can actually take a look at in our model. You may not be practical to run like a 100-year simulation with the FDC, but at least if you want to see what will happen under, under a climate change scenario, you could put those factors into your boundary conditions, and you would be able to predict what might happen. So with regards to salinity, many of you are probably familiar with how that functions. This is a longitudinal slice of a theoretical estuary here. So because of the density differences between saline water and fresh water, what you'll typically see is a wedge of saline water pushing in the bottom of the estuary. And then depending on how much flow is coming in, that will kind of cycle fresh water out of the system. So that's a dynamic that we're going to see in our example today. So as that says. So open boundary conditions. I've seen a lot of models that have very poorly configured open boundary conditions. That's actually one of the most common problems that I see when users will post their models on the forum, or when they'll send their models to support, is just poorly configured boundary conditions for an open boundary. This can have all kinds of, cause all kinds of funny things to happen in your model. You can get jets of water that seem to appear out of nowhere and have fraud numbers that are on the order of critical flow in a very deep open ocean area, and that makes no sense. That's not something that happens in nature. So depending on how you set up these open boundaries, you can get some pretty bad results. What's important is to configure them properly and kind of know the different things that you need to do in order to make these open boundaries behave realistically. So typically for an open boundary, you're going to have some knowledge of what the tidal conditions are in your system. You might be, if you're close enough to an ocean, excuse me, you might be able to use harmonic constants to predict the tidal, to predict your tidal boundary. You might also have directly measured the water surface elevation near your open boundary, and those could be directly input into the model. So you have a couple of different options there. Most tide stations in the United States will give harmonic constants for that station that are used by NOAA and other agencies to predict water surface elevations there. That said, there are some systems where these harmonic constituents are provided, but say the tidal station is far enough upstream in a low-lying river estuary that the discharge will significantly affect the characteristics of that tidal signal. And so the harmonic constituents won't really do you any good, because the river is playing such a large role in that system that you can't really ignore the effects that that large river inflow is having on the water surface elevation. There are a few different options for the setup of the open boundary, which we'll be talking about later. So and we'll be talking about them right now. So elevation specified, as I said, this is basically direct input of the water surface elevation, and that is a forced condition. So no matter how much water needs to be let in or out of the model domain, if you have it set up in that way, it'll make sure to maintain that water surface elevation at that boundary. Radiation separated, zero tangential. This uses the water surface elevation gradient instead of a specified elevation. So it'll be looking at the gradient of the water surface elevation just upstream of the open boundary and trying to maintain that gradient through the open boundary. How you specify the water surface elevation there. This would allow the energy from waves to pass out of the domain. Sometimes with the elevation specified, what you'll see is waves will reflect off of the open boundary. And yeah, the radiation separated free tangential is another option as well. You can read about right there. So best practices for setting up open boundaries in EFDC. Don't do this. This will cause what I was telling you before. It'll either the model will crash right away, or you'll get some crazy velocity patterns that will not be realistic. So what we generally recommend doing is to kind of notch out. So say we have, in this example, we have 4 open boundaries here. What you want to do is kind of notch out 2 to 3 cells around each corner. Say your open boundary is kind of a square here. You want to notch those out. And then also, you want to flatten the bottom elevation for the 2 interior cells. So whatever the bottom elevation of this cell is, we would have the same bottom elevation in this cell and in this cell here. And that will just allow smooth transition into the model domain for that open boundary. Yeah, so when so transport of constituents in an open boundary. So when we have a temperature or a constituent time series, say a dye time series set up at an open boundary, if water is flowing out of the domain, whatever is in the water just upstream of that is going to go out of the open boundary. So whatever you assigned as that boundary condition temperature or dye concentration won't matter in that condition. Now, if water is being allowed in by the open boundary, that's when that temperature or that dye concentration will be specified for the water coming into that cell. So we talked a little bit earlier about how those data files might have been put together. So I'm just going to go through quickly where you might find some data to put into your coastal and estuary models. So NOAA has the general bathymetric charts of the ocean. These would be really useful for setting up a coastal boundary, a coastal model. We also have other data sets available through the NOAA. Several different sources here for bathymetry. University of Washington has a great data set for Puget Sound. You can find a lot of bathymetry online. Global tide models, there are several of them available. The United States government puts out several of them, depending on where you are. AdCirc's one example for the eastern, for the Western Atlantic. Wave data as well from NOAA. NOAA has a huge amount of data. Some of it is kind of hard to find. So if you need to reach out to somebody at NOAA, likely they have some of the data that you might be looking for if you're looking at a coastal model. Yeah, they have tons of buoys, tons of different instruments out there in the ocean that is all that data is freely available. It's just a little bit hard to find on their website. NCDC, this is a great place to get atmospheric time series data. This is kind of my first stop when I'm looking to put together an atmospheric time series. CDO, this is the system where you can actually download data for specific observation stations. Usually those are most commonly at airports. Weather Underground is another potential source of data. And then, there are a number of sources which you can get weather data from. Always quality check your weather data. I can't tell you how many times I've seen bad data make it into a model. Always plot it. That's the key, actually, is once you get it into your model input files, plot that data up, ask yourself, does this make sense? Is the temperature increasing when the sun is up? These are just kind of common sense checks that you can do on your data to quality check it. Yeah, NOAA tides and currents. This is kind of the central place to get not just time series data of observations, but also harmonic constituent data for a particular station. The NOAA shoreline database, USGS gauges, these are a favorite for any kind of model that we're putting together in the United States. USGS data is really easy to access, not just through their online web portal, but they also have great API features as well, so you can script your retrieval of data very easily. As does NOAA, actually. One of the things that I want to mention about NOAA that's kind of a little bit irritating is that if you want full 6-minute resolution tidal water surface elevations, you can only download 1 month at a time. So imagine trying to put together, 10 years of data if you were doing that just by downloading 1 month at a time. It's insane. So, what I had to do is actually had to use their API and create a script that went out and asked for 31 days of data at a time and then stitched together afterwards, which shouldn't really be necessary, but, I guess they just have these features to make sure that people don't overload the system, I guess. I'm not really sure. INWIS with the USGS, these are, again, very, very good sources of data, quality check data in most cases. They could have significant gaps, however. A lot of times in USGS stream flow data or stage data, you might see gaps of several years in those time series. So, if you're going to be putting together a model, definitely put together a big chart of all of the time series data that you have and see which periods actually have full coverage for all of it. Because if you're getting data from publicly available sources, you might just have to be dealing with those data gaps or find some other way to fill them. And now it's time for our hands-on exercise. So, you guys have any questions that you want to? Yeah, please.
Well, with the sea level rise, this can be your input for the estuary model.
Right. So you could put that together. You could put that together yourself as a boundary condition. Say say for example, you have kind of a typical tidal pattern from an estuary that you're interested in. And you might want to see what happens if there was, say, 20 centimeters of sea level rise at that location. It's really easy in the Explorer, actually. You could just add 0.2 meters to all of that data, to every single point in that data. And then the sea levels will all be 20 centimeters higher. And so you could look at what a typical day might look like. Yeah, exactly. Yeah, you can just make scenarios like that. You can add and subtract from any time series data in the Explorer and just save out the input files again, and you'll be ready to test that new scenario. If you wanted to set up say you have a pretty fast model and you want to do some long-term simulations, say you're going to predict that the sea level will rise 20 centimeters over the course of 10 years. You could just apply, a simple linear relationship to your existing data and say, okay, the next 10 years are going to look like the previous 10 years, except by the end, we're going to be on average 20 centimeters higher. And you can just apply that to your open boundary condition and run that simulation. Yeah.